Welcome. And in the last thing that I talked about, the last session, I focused primarily around hardware. And just to give a very quick overview of that, there are devices that make up the computer system. They include the inputs and devices that get information into the computer, the output devices that allow us as humans to work with the computer and see what's going on. Internally, there's something called a processor that does calculations and computations and moves information around. There's an internal memory that holds information while it's worked on, and then external or internal, doesn't matter where it is, but storage that allows us to store the information for the long term. And I talked about different strategies for storage. So it gives you an overview of the world of hardware. What I'd like to talk about just a very little bit is the nature of software. The problem we have here is that it's actually very easy to touch devices and see how they work and understand them. They're kind of intuitive. Software is not intuitive. It's not an obvious thing to us. It took, in fact, until the 1940s for concepts related to programming and software to really emerge from work that was done by scientists during the war mainly. So software is a relatively newcomer into the world of equipment. We have devices that are similar to computers or do calculations that go back for hundreds of years, some even further. For example, the use of the devices by the Chinese to do calculations, the abacus and other devices, logarithms. You may remember the use of the slide rules back in the 60s and 70s, where people used slide rules. So there were calculation devices around for a very long time, but the ability to write programs and to conceptualize the programming of a system is brand new. It's only about 60, 70 years old, so it's a relative newcomer into our lives. What we're doing with software is putting instructions into the memory. So if I took this circle thing here I called memory and I expand it out so you could see kind of like what it looks like. And this is just analogies and so on that I'll use here. But if you think about the memory being a bunch of slots, and it could be a shelf in a mail, like one of those mail things that you sort mail into. If you think of the memory as just being a stack of those kinds of shelves, it gives you a pretty good idea of the way it works. For example, I could put an instruction into a location here by using a code that the processor can understand. That instruction could say, get a number. Okay, get some number. Where? Well, let's call the location here number 1, number 2, number 3, number 4, and 5. So I say get a number, and where is that number located? Well, let's say the number is going to be here. So the number 1, 3, 5, 7, and that's a get the number that's in location number 2, basically. So we have an instruction that I put in there in the form of a binary code. This might be symbolized by some bunch of zeros and ones that says, essentially to the processor, get the number that's in location 2. And then it might say another command here, next down here, is get the number that's in location 4. So it's got a number here of 1111 in location 4. So this is a command in coded form, again, some series of ones and zeros that tells the processor to go get a number, which happens to be 1,100. I'm doing it in decimal to make it easy. Get this number here in location 4, and then do something with it. So the next thing I put here would be add those two numbers. Add location number 2, what I got out of number 2 and number 4, add those two numbers, and put the result in location 5. So next location, result 6 in this location. That is a concept of a simple program. So what's interesting here is that there is a mixture of numbers that are used as numbers, like this one here, and numbers that are used as instructions in one set of slots. And what I have to do in order to be able to write a program is organize my thinking in this kind of way and put things in very literally like I would put them into slots. So the processor starts at the top slot, number 1. So it goes right here, and it says, get the number in location number 2. Okay, it gets the number in location number 2. And actually what it would have to do is then say to skip a location and go to this instruction. So this is a kind of a silly program here. So it then says get the number that's in number location 4, which happens to be this one. And then I have to tell it skip a location and add those two numbers and put the results somewhere. So it's a very sequential process that goes on. And typically what one does, instead of the way I've done it here, you put your, in one set of memory locations, you put your program, get this part here, get this number, get this number, get this number. You put those things in sequence. So you got this, this, this in sequence, and somewhere else in the memory, way down here in the stack, you put the numbers themselves, and you keep this separation between the numbers 1, 3, 5, 7 and 1, 1, 1, 1, and the result, which happens to be whatever that comes out, 8, 6, 4, 2. 8, 6, 4, 2. So you put them in separate locations. So the processor could then deal with only these instructions, one after another, and when it got to the end, there'd be something that said stop, and the numbers would appear in these locations. This might be in location 1, 2, 3, 4, and this would be in location 101, 102, 103, and that would keep the two sets of results separate so we don't get confused. And this is interesting, right, what I've done here, and the reason I broke it out here is that if you wrote a program like this, where you've mixed together numbers with instructions, there's no difference in the computer memory between these numbers in terms of what they really look like in the computer. There will just be different patterns of ones and zeros. What that means is that with a program, I can actually go back and modify an instruction, and it could destroy it. So instead of executing, or the processor executing this as an instruction, I could mistakenly send this instruction as a number and tell it to get added to that instruction and get a result, and that's a totally meaningless process. The computer has absolutely no way of knowing that. It's simply due to the order on which I do things and the locations where I put them. So one thing that can happen in a program is I might start it in such a way that it treats a location as a number, and then it just produces garbage. And sometimes when programs fail, that's exactly what's happening. The programs have modified themselves, modified the numbers, and produced utter garbage in the process. So if you get an idea from this that programming is a very meticulous process, it is. That it's easy to make mistakes, it is. That any kind of complex program is very difficult to write, that is true. You get some idea that developing software is a very complex art. Now, if we had, when I first started working with middle 1960s, the way we in fact programmed the computer was we put these ones and zeros directly into the memory location. We used switches on the front of the computer. Put one down, one up was a one down was a 1, and an up switch up was a 0. And then we loaded that number into a location, literally, in a single step. And that's how we program. And of course, even to add two numbers takes a whole bunch of instructions and a certain amount of ordering of the information so that it doesn't screw up or I can understand what it's doing. So doing simple programs using that method, where you're programming, if you want, with the number system of the computer, is ridiculous in today's terms. We don't do that anymore. So next thing that happened in the evolution of software, instead of loading these numbers directly into the memory locations, and by the way, the original computers had very few memory locations, instead of doing that, what we did was be able to, for example, write a program using something called an assembler, which allowed me to write the program in something like English, which was something like, get a variable, get a number, like I've written over here, get a number and where the number is, wherever that might be, and get another number and wherever that is, and then finally add the two numbers. I could write a program using this way instead of loading the numbers directly into the memory locations. Well, at least now I can read it. So if I screwed up, I can see how I screwed up very much more easily. And there's none of the labor involved in entering these numeric values in through switches or other technologies. So assembler was the earliest method of really making programming easier to do. And still people use assembler for particularly related to devices where you have to program devices like washing machines or television sets that contain processors. There are types of assemblers that may be used in certain situations. The next step was to say, this is still too meticulous, this is crazy, and what are called higher level languages have been developed. These are much more like English. Examples of these are Fortran and BASIC, today Visual Basic, Java, other programming languages exist, which allow people to write in something much more understandable. And what happens then, with an assembler, we had then, this would go into the computer, which had a program running that would interpret each of these words into the appropriate numeric instruction that went into the location in the memory. So instead of my having to memorize these codes, this would translate from this sort of pseudo-English into the code for me, making it less likely that I would simply mess up by putting in the wrong code into the memory location. That program was actually the assembler that did it. This is the assembly language, was running in the processor. It was not a hugely complex program, but it worked extremely well and made it a lot better. Go one step up and you've got something even closer to English, but with a lot more power. So what we've got is, again, in order to program using the higher level language, we have some sort of program running in the computer that takes this description in English that I write and runs it through this interpretive process and takes that English-like stuff and turns it into the codes that go into the memory locations. So today, all of our programs, pretty well, that we deal with are written in these higher level languages, some of them extremely sophisticated, and sometimes even with ability to do some of the things using arrows and Visual Basic, for example, using symbols instead of having to write every command out and create a flow. It's a lot easier to use these languages. And common mistakes can also be detected. So if you misspelled a word or tried to carry out some function that was inappropriate, there are some of these that can be detected in these higher level languages that prevent you from making at least the simple mistakes that might be possible. All right. So we have a series. We started with simple numeric representation of programs directly loaded into memory locations. We then created something that allowed us to get a little bit more like humans could deal with, that ran, where a program ran and interpreted this into these numeric representations. Then we had these higher level languages that make it even easier to do write programs and put them. There's again a processor-based program here that translates this into this same material here. So we've moved a long way, but this deals only with what the human produces, and the human can make incredible mistakes. In other words, if you write a program, you can just ask the computer to do the wrong thing, and sometimes it's not at all obvious what it is. That what you've asked the computer to do is just dumb. So, broadly speaking, pretty well every program written by people has built into it mistakes. Errors, we could call them mistakes. Commands that are inappropriate to do at a certain time. It's not what you really wanted. You gave the machine, in the higher level language, you gave the machine to do something that it really is not appropriate. So instead of multiplying two numbers, you added them. I mean, that's a mistake. and you just happen to use the wrong symbol in your program. And the program may even appear to work. So almost all the software, if not all the software that we develop today, has these mistakes in it. Now, many of the mistakes can be found through testing. So I run a program and I put data in and I see what I get out. And if it doesn't produce what I want, I can see it and say, oh, where did I make a mistake? Oh, on line 5,432, I told the thing to add instead of multiply. Simple mistake. The difference between maybe putting a plus sign versus an asterisk between two numbers. I mean, it can happen. So I test the thing and I see, okay, and I detect that. So I do testing during the software development process. It's part of the software development process. The trouble is that some of the programs, many of the programs we write today, are enormous. They contain hundreds of thousands or millions of lines of code. In other words, instructions like add two numbers contain millions of those instructions. And many of the programs deal with many different circumstances. For example, if two numbers are less than 100, I might do something with them. If they're greater than 100 but less than 300, I might do something different with them, and so on. So I can have many, many, many cases of possibilities, including extremely rare cases where someone, instead of entering a number into an addition, enters a letter. So they hit the letter A on the keyboard instead of the number 1. They just happen to be, well, Q instead of 1, which are close together on the keyboard. That happens maybe once in 100,000 keystrokes that you would do that. But if you were entering something and that would come up, well, now that unexpected mistake will cause your computer program to try to add the letter A to 1, which is a meaningless thing, and it will cause the program to produce garbage. So it will cause the program to crash or to fail in some way. So we end up with the potential of many, many places in these large programs where pieces of code, groups of code, are executed only rarely, or certain types of errors can occur, they occur very rarely, and that during the testing I do, I may not have tried that particular combination of events, so that the program that would show an error doesn't show an error because I don't test that specific situation in my software testing. Now, I should say, with people who do software development, they've got enormous capabilities for testing. They've got suites of test data. They've got a very sophisticated approach to that. But despite all the human effort that goes into that, despite every attempt to find every mistake, pretty well all programs harbor errors. You see it periodically. You see a program that crashes on your machine. Why? Well, could be a certain set of events occurred that the developer did not take into account. Could be certain data came in that was not expected data, and it had not been tested for. It could be almost anything you can think of. So buried in this millions of lines of code. Oh, another example would be where you have security updates that you get for your machine, that the vendor that sold, like Microsoft, that provided the Windows or whatever it might be, hadn't taken it into account that a hacker could find a certain way of making the machine behave in a way that allowed the hacker to take control over it. They just hadn't figured that out. And as soon as the hacker does it, then they can put in a fix, sometimes called a patch, or a new version, or an upgrade, or something like that. So you have constant updating of our software to deal with new potential mistakes, which are threats that we didn't eliminate during the software development process. If you get the idea that all software contains these errors, they're also called bugs, then you get the idea that we're in a metastable world with software. There's always the potential of failure, and it's only the degree of testing, the number of people that use it, the length of time that it's used, that fewer and fewer of those mistakes or bugs or unintended consequences get found and addressed. Then you've got the idea. So that's the nature of software, an imperfect aspect of human nature. Very rarely do we find that in hardware, that the hardware has a mistake in it. There have been mistakes, though, in hardware. I used a computer early in my work that did a calculation that it was not supposed to do. And it actually was very useful. It was a mistake in the way the electronics were set up that allowed you to do something you weren't allowed to do. And people use that. You can imagine when they finally would correct that error, then none of those programs would work, because you used sort of an off-label use of the codes that you had for the computer system, and they failed if that error was corrected in the hardware. So hardware can have errors as well. And but really, most of the errors occur in software, and I said they're called bugs. And that comes from back in the Second World War, where Grace Hopper, and this is actually at the one of the national museums in the United States in Washington, D.C., they had a problem with one of their computers, and it turned out there was a moth inside the computer. And they took the moth, they don't know if it caused it or not, but they took the moth out and glued it into the book. And from then on, software mistakes were called bugs. And this happened to be probably more like a hardware mistake, but if it existed at all. But that's where the word bug came from. So bugs are these errors that live in these software, in all software, and can express themselves at any time. And this is, by the way, one of the things that concern people about the use of programs to control military capabilities. One example was during Ronald Reagan's reign in Washington, the development of Star Wars, where software was going to control shooting down incoming thermonuclear warheads. And a famous software engineer said, we're finally going to fully test that software in the first 15 minutes of a thermonuclear war. And likely there would be problems. So it was a rather devastating outcome if that software didn't work, and it was highly likely not to work in that situation. So that's why you get upgrades or updates to your software. That's what it's about. That's how it works. With respect to programs now, programs can be of many types. I've already told you a couple of types of program. One is this assembler. It's a program that translates pseudo-English into numeric information, puts it in the memory of the computer. Higher level languages just are more sophisticated. They're nicer. They say add A plus B instead of having them on separate lines and going through all these steps. There's a program that translates that English-like stuff into the same thing that goes into the memory of the computer. But there are also then programs that we write that do useful things for us beyond the programming of computers. For example, I can write a program that would allow me to input a bunch of numbers and then display them in a list. In fact, I could display them in a matrix of, in other words, columns and rows. And what's more, I could write a program that would allow me to add any number to any other number just by saying, well, add column 1, row 1 to column 3, row 5, that number in those locations. And that's called a spreadsheet program. So spreadsheets are a way of doing particularly numerical processing using a concept that was really brought to the world by VisiCalc, no longer in existence, and has now been succeeded with programs like Excel and other alternatives that allows us to deal with huge amounts of information in very simple ways, and allows us to change information without changing the way we process it. So I can put one group of numbers in and I can get a statistical result, put another group of numbers in. I don't have to change the statistical program that does the analysis, that calculates the statistical results. I can just put new numbers in, and I can have the ability to modify those numbers and do what-if kinds of calculations. Let's say I have a list of numbers. What happens to the result if I add 1 to every number? So I vary the numbers a little bit. What happens to the result? How much does it vary? Does it explode, or does it just vary a little bit? So I can do that type of calculation. I can write a program that allows me to capture text. So I hit the keys on a keyboard, and allows me to put those those letters into memory locations, and allows me to go back and change one of those letters from A to B, for example, or to add a letter in between them, which would involve, if I put a letter in a memory location like here, and then I had the letter A here and the letter B here, and I wanted to put a number in between. What I first have to do is move B down here and then put something in between, in that memory location in between. So I can insert, I can delete. That's called a word processor. And of course, word processors are much, much more sophisticated than that, and today themselves involve certainly millions of lines of programming code in order to do something like Word. And be able to do all the things we want to do in word processing. So these are called applications programs. One is a numerically oriented applications program, Word. Another is a numerically oriented applications program, Excel. The other is a textually oriented program, Word. But they're just applications programs, and they're usually called, as a class, productivity tools. In other words, these are the things that allow us to quickly create documents, to quickly do calculations and do analysis of information. Of course, there are many, many kinds of productivity tools beyond that. There are programs that allow us to do emailing, programs that allow us to do presentations, for example, PowerPoint. These are all in the class of productivity tools that we use, and they are one of the class of applications programs. So applications program at the top, and then below it is productivity tools. But then there are other types of things under applications software or applications programs. Big example is all the programs we've developed in health settings. For example, we have a program that we might use to calculate like a body mass index. That's a real simple applications program. You put in the weight and the height of a person, and it calculates for you the body mass index. There's a very simple program that probably a person with very little training could write that in a reasonably good way, and so on. Okay, that might be part of a bigger program which helps you to manage your lifestyle. So there's a whole area called lifestyle maintenance or health maintenance that calculating your BMI, so as your weight changes, your height won't change, but your weight changes, then your body mass index can be recalculated. So you watch it as it gets more into the normal range if you're a bit overweight, for example. So that's an example of a much more complex program, because now a lifestyle program may keep track of the number of hours you exercise and what kind of exercise you do, what you eat, so your nutrition, when you eat. It might keep track of particular medical parameters for you beyond the BMI, like your heart rate after exercise for an hour or something. So that type of program can become very, very, very complex, and itself can be certainly hundreds of thousands of lines of code to do that, maybe even more. But it can go up from there. Another type of, in this class of application software for health, or programs for health, is the area of departmental information systems, DIS. For example, laboratory information systems, or pharmacy information system, or any of the other information systems that are around, radiology information system. These are very complex programs that help to do a number of things. One, they help us to register patients as they come in, or their samples in the case of labs. They help us to manage the operation of a department so that all the things that go on can be managed. Managing a radiology department, for example. They can help us to do things to patients directly, for example, to provide meds and to look at if a given medication might interact with other medications the patient already has on board. So they can do very complex things and maybe even provide feedback to say the medication you'd like to give the patient has side effects. Perhaps you'd like to choose some other medication for that type of patient. These are at another level of complexity. Certainly millions of lines of programming code are involved, maybe even tens of millions. So these are big programs. They cost a small fortune, big programs for a small fortune. It's hard to buy many of these systems for less than hundreds of thousands of dollars, although there's sometimes simple versions of them that can be bought. To go one level of complexity up now, you combine all of these systems across, all of them now, across a whole institution, and look at something like a hospital information system. Now you're talking a gigantic program that is enormously expensive. Back in the 90s, I worked on a project that involved estimating what it would cost to build, at that time, a hospital information system. And the numbers we came up with a major consulting company in the United States was between $50 and $80 million to create a hospital information system, a comprehensive one. So these are big deals. They cost a lot of money. And they are combinations of many, many different individual capabilities that are made to work together and communicate with each other so that information can transpose between the different systems. So the laboratory information system can ask for information from the admitting discharge transfer system. The pharmacy information program can look at the laboratory results of the patient to see if a medication might be a problem. For example, if there's poor kidney function or liver function. So we have a tremendous ability here to build this thing. But the message is, if in simple programs I can make errors, you can get some idea that within these programs there are many, many as yet undetected bugs that could show themselves at any time. And one of the big issues we have related to this is the ability to assure ourselves that these programs are reasonably without these bugs, or where they show themselves extremely infrequently. And there's now a new science called systems assurance. Typically the schools of accountancy are involved in this, and there's a Center for Information Systems Assurance at the University of Waterloo. What they're trying to do is build software so that we build it in such a way with tools and with built-in capabilities that we know exactly what it will do, that we can predict it and count on it to do exactly what it is. And you see why accountants might be interested in that. If you could use a financial system for fraud, where you put the wrong information in, but would it be even more interesting to take a financial system and modify the programs so that the programs did the fraud for you? And we don't know that when you're looking at a balance sheet for a company. It could be fraudulent in a number of different ways. So even if the programs seem to be correct, they could be modified. They could be, or they could have inbuilt fraudulent code in them that cause certain things to occur and bury certain things that we're doing. So information systems assurance really looks at the issue of creating this type of software. And information systems assurance is close parallel with an area called software engineering. I've talked here about programming and very simplistic ideas, and I programmed for many years. But I can tell you, I never wrote a program in my entire life, and I did tens or even hundreds of thousands of lines of programming, that was a good program. And the reason for that is I had no idea when I did my work that a field called software engineering would emerge, and that there were structures, that there were ways of writing programs that made it more likely I would produce what it was I wanted, and less likely I would make mistakes. And as the programming complexity increased, I was able to keep the quality. So software engineering has emerged where people learn discipline around the art of programming, so that what is produced is represents what they want, does what they want, and is where you look at things like bugs as being something that you systematically eradicate through those processes. Think of the bridge you're building. It's going to bear, if you're building a bridge, it's going to bear weight. People are going to go across it. And if it isn't built properly, it will collapse, and quite a few have over time, not least of which was in Minnesota, where the bridge just about 2 years ago now collapsed. The engineers build those bridges. They have standards. And if those standards are followed, and if the bridge is maintained, the warrant that we have is that the bridge is built and should, if everything works the way it does, physics and not too much salt, injuring the beams and things like that, then this bridge will stay up. In other words, if it's properly maintained, it will stay up. So engineers do that using the science of engineering and the practices of engineering. The same concepts apply in software engineering, where you're building code that is solid, that will stand up, that won't break down and show errors, create problems with the future. So software, people talk about hardware and software. I say software is really the hard part of developing systems. The people who are involved in that, programmers, write code, some systems analysts. Today most programmers are both systems analysts that break down and understand processes, and also are people who write the actual programs. Usually they are trained in software engineering, and typically leadership is expert in software engineering. There are methodologies of programming that are structured processes to make sure that things are done well. One of those is maybe worth mentioning. Much as I mentioned, there's some architectural niceties of the use of storage devices. The area of software and the development of software has really moved beyond some of the original concepts. We now have, call it software management techniques that take into account the fact that we are developing things today which are highly innovative, and we can't, before we start the whole process, write down in a requirement, as it usually is called, a requirement specification, everything that this thing is to do and every way it's to do it. We just can't do that. We don't know. We have to discover things during the process. And things like agile development or agile programming have emerged that look at software development as an iterative process. In other words, where you do it, part of it, you evaluate what you've done, you fix it, improve it, do that, and keep doing that. You look at software development as an iterative process rather than a once-through process that old software development did. It was called waterfall approach, that you did one step, and when that was done, you did the next step, and you never really went back, and you kept going until you were done. Today's programming is very much iterative, so you do a step, check it, make sure it works, go back and improve it until it's working, and then drop to the next step and keep doing things that way, with the result that we end up with systems that are really tuned to what it is we want them to do. This has become essential because if you look at large-scale software projects, they fail at an incredible rate. There have been many examples of this. The FBI in the United States, or the justice system, tried to develop software. It was a catastrophe, I think an order of $1 billion catastrophe. The Federal Aviation Administration, same thing, ran into just huge problems because what they're trying to do is so complex that it's just right at the limits of human ability, and there are these newer approaches to developing software that allow us to, instead of assuming we can do it perfectly from the beginning by properly and totally specifying it, allow us to do it in these iterative steps where perfectibility is a process instead of a do-it-once type approach. I guess beyond that, in order to make just bring this back to some of the interests that people might have, we're seeing programs develop that go beyond the operation of supporting the operation of departments and into working with human beings and carrying out human functions. So within a hospital information system, for example, there might be something for computer-based physician order entry, or CPOE. And it isn't just a matter of that being a program that captures an order from a physician and sends it to the lab or the pharmacy. But rather, these programs today often have embedded in them a degree of intelligence, not human intelligence, sometimes called artificial intelligence, but machines that can learn, and machines that can help in decision making, sometimes called decision support systems, are often built in here. So if the internist orders a lab test that was just ordered a few hours ago, the system might remind that person. You can always override, but it says, that just got ordered. Why are you doing it again? Or you've got a diagnosis in the system of whatever the diagnosis is, and you order something that's inappropriate for that diagnosis. The system can ask why. Again, you can override it, but it could catch all kinds of errors. For example, giving the wrong medication, the wrong dosage, ordering tests that expose patients to radiation that are unnecessary or that run up health system costs for no purpose. So what we're seeing is, beyond operations support and documentation, is these little areas within the software systems where the representation of some of the capabilities of human intelligence is implanted, and where these programs really help humans in their cognitive functions, particularly if you're busy, a lot of information is involved, and and people's lives are at stake. Examples I mentioned: computer-based physician order entry, sometimes separate diagnosis support systems that help you to make diagnoses. There are systems that give advice on therapy. One example of this that's very important is the guidance of chemotherapy and other cancer treatments. So, because very complex protocols are involved in that, so a series of things that are supposed to be done that are often forgotten. So what we're learning to do is to actually build into this software, again, yet another level of complexity, build into this software capabilities that are human-like, and that we've gone into the realm of helping directly, not just operationally, but in the cognitive aspects of practice. And one that might be of interest to, for example, people in health information management is the area of the coding of charts summaries at the end of care. So we have programs called autocoders that are able to take data, which would be there in the electronic record, and be able to take that data and like what events of care occurred and so on, and automatically code that to cut down the effort of the coder. And I've seen research papers on that show significant improvements in from years ago, to the point that auto-coding can be as good as the average coder. Not as good as really sophisticated, highly capable coders, but as good as the average coder. And that's something that really may make a huge difference in cutting down the work associated with coding and producing, for example, data for Canadian Institute for Health Information. So that ability to have these human-like capabilities in programs can make a huge difference in work. And this is yet another issue that comes with software. Software is where the systems hit the person. That's what you interact with, in fact. Through a device, you interact with software. So you're giving input to a program. The machine's underneath it and capturing the stuff and putting it in, but you're giving input to a program. And those programs can have errors. We've talked about that enough. The fact that you're using that program may have legal and regulatory consequences. For example, if you have a patient directly use a computer program for chronic disease management, that attracts regulation. So there are qualities that program must satisfy in order for you to do that legally. If you create a patient portal, for example, allowing patients to manage their diabetes or heart failure, that's like a medical device. It's like giving the patient a medical device, and there's no clinician between the program, the software, and the patient. So suddenly this has become an agent of care. It's an interesting reflection. We've moved past the point where systems are just there supporting operations. Now they're like a provider. They're doing some of the things a provider does. And some of them are built right into us. For example, if you look at implanted defibrillators, the implanted defibrillator concept is doing what a doctor used to do on the outside of your chest, right in your heart. And you're dependent on programs that are looking at your heart rhythm and deciding if you're in fibrillation. And if the program decides you're in fibrillation, it zaps you and can knock you to the floor. I mean, we've really gone past the idea that these are passive devices. They've become agents in care. It's like having an implanted person that's doing defibrillation. Pacemakers, same thing. Insulin pumps, same thing. Brain stimulators, the same thing. So it's a huge change from the time that all we used these things for was calculators, and into the time where they have become, in fact, active agents in the care process. So it's a big deal. Again, related to this topic, I point you to the opportunity that exists at the questions and answer sessions each month. There's also the blog. So if you have any questions or any thoughts, put them in the blog, ask the question online, whichever way, and let us know. It's easy for us to either answer them at the time or to create additional material. We're in the process of creating another bunch of material. It actually is a bit old, that material, but it's will be on our system in a little while, which it goes through this stuff in a bit more detail and gives some additional ideas. It was filmed at the University of Manitoba, and it was created by their AV lab there, and it's been actually on television in a number of jurisdictions. So you may find that also to augment this, assuming we get that fully online for you. So I'm at this point left with questions that you'll have to ask. Before I leave, though, I would like to point out that one of the things that we will do in the future is to look more deeply into this communications links, particularly in how the internet works. So one of the follow-up presentations eventually will be the nature of the internet and how it works, so you can get some understanding of why things work the way they do and what a brilliant invention the internet is, which has totally changed society, created online businesses that no one could have dreamed about, and brought everybody on Earth so close together that distance almost doesn't matter. So that will be another one that we will talk about. Beyond that, though, we really minimize the importance of hardware and software and the applications software that's built on the concepts of programming in this series, because what you'll find out is most of what you do in applied health informatics, this stuff is served up to you. It's only important to know the concepts. It is not at all important to know how this works. You do not need to know about programming. If you want to get into programming for fun, you can do that. If you want to get into program for health, my suggestion is you formally study computer science and software engineering. Otherwise, it's sort of like building bridges without the background in engineering, in that case mechanical or civil engineering that's necessary. So the counsel to you is that most of this is just interesting information, and you can forget it pretty well once you're comfortable, sufficiently comfortable that you don't really find yourself concerned about how all this stuff works. So thank you very much. It's been enjoyable doing this, and I hope of some value.